When I was a student learning control theory at university, I started to form an idea of what a control engineering job looked like. What was I going to be doing as a professional in industry? I thought, well, I'll be designing controllers, right? Well, it turns out it's more than just that, and even designing controllers is different than I thought it would be. So in this video, I want to share 5 misconceptions that I had as a student in the hopes that it helps you in some small way prepare for a career in control engineering. I'm Brian, and welcome to a MATLAB Tech Talk. I want to start by saying that controls is an incredibly diverse skill, and you can end up in any number of industries, as illustrated by this wonderful drawing by Margaret Bauer. Now, my background is aerospace, but keep in mind that these misconceptions will exist in some form everywhere. All right, let's get started. First off, I think it's common for students, and certainly it was for me, to think that in industry you're always going to be trying to design the best thing possible. You're always going to implement the latest cutting-edge technology to try to maximize performance. For example, for a control system, I thought that if I designed a controller that had this response to a step input, where you command it to go to some goal and then it rises up nice and easy, and maybe overshoots a bit and then settles down, that in industry, this is objectively worse than a controller that has this faster response with no overshoot. I thought, I always want to go after this better response, even if it means implementing a more complex controller. But in industry, this isn't the case. The best controller isn't necessarily the one that has the best performance. It's a controller that does exactly what is asked of it, and no more. It meets the requirements of the project. And the reason why you don't want to design something with more performance than you need is that it's easy to lose sight of the fact that it typically costs more to improve performance. And for a control system, these costs come in the form of needing better sensors, stronger actuators, and more compute power. Plus, you have to consider that on the algorithm side, simpler ones are easier to tune, test, and verify. And so if the project doesn't need it, you might be doing more harm than good by trying to improve your controller's performance, or by implementing a more complex solution. Therefore, when you get to industry, you're going to find out that the best controller that you can implement is the simplest controller that you can get away with, or the simplest one that still meets the requirements of the system. And speaking of controllers, my second misconception is that when I was a student, I thought that in industry, the majority of my time would be spent actually designing controllers. And I think this misconception comes about because as students, we're often looking at relatively simple systems. And the nice thing about this is that we can use them to learn the fundamentals of control theory without getting bogged down with too much complexity. We can learn how to design a controller without needing deep knowledge in modeling and linearization, or even hardware and software implementation. And this is great. But the downside, at least for me, was that this is what I thought control engineering was. Setting up the problem was easy, and developing a feedback controller for it was the time-consuming part. And therefore, I thought this was the same in industry. I'm going to be given a model, or that, developing a model will be straightforward, and then from there, I'll just spend most of my time figuring out how to control it. But real systems are often more complex than an inverted pendulum on a cart. This means that to even get to a model that you can use for controller design isn't straightforward. And beyond modeling, there are many other problems that we get to solve as control engineers, from building and running tests, estimating the state of the system, and picking the right components, just to name a few of them. And this variety, I think, is a lot more fun than just designing controllers all day. So just keep this in mind, that the majority of your time will be spent designing the entire control system, which consists of more than just the controller. All right. So another thing that I failed to understand as a student was just how interconnected controls is to the entire system. I had a misconception that if you want to be a control engineer, you really just need to learn controls. Around my junior year, I already knew that I wanted to be a control engineer, but I still had to take all of these other classes. And I thought that since I didn't need them to be a control engineer, I'm not going to pay attention. But this couldn't be further from the truth. In fact, most everything you learn can be applied in some way, and I wish that my engineering professors had emphasized just how interconnected all of these disciplines really are. Let me give you an example. On a spacecraft that I was working on, we were in the early stages of design, and I was asked where I wanted the inertial measurement unit, or the IMU. The IMU is just a sensor that consists of an accelerometer, a magnetometer, and a rate gyro, and the attitude control system uses it for closed-loop pointing control. So, where to put it? Now, even though the spacecraft is a complex system, my mental model of the spacecraft looked something more like this. To me, it's just a three-dimensional mass that I want to rotate using torques from the reaction wheels. And so what I needed to know was how that mass was rotating. And so to avoid the cross-coupling between acceleration and rotation, the best location for me was to put the IMU right at the center of rotation. But this type of thinking ignores the fact that a control system needs to function alongside other components in the spacecraft. I should take into account temperature and vibrations and electromagnetic interference and system integration throughout the entire design process. In this way, my decision required some amount of system-level knowledge. And it turns out this is the case with many decisions that you're going to make as a control engineer, because your control loops will touch many different systems, from the mechanical components to the electrical and signal components to the software. So instead of thinking that you only need to learn the one discipline you're interested in, try to remember that a system is the product of multiple disciplines. And learning from different fields gives you a better understanding and broader understanding, and helps you solve those unexpected challenges. So I'm encouraging you to learn as much as you can in every class that you take. All right, the fourth misconception that I want to address is that I had this idea that doing something yourself is better than using something that already exists. For example, I thought it's better to write your own PID controller rather than use the pre-built PID block in Simulink. Or that it's not real engineering if you're just starting from somebody else's code base and making small changes. Or increasingly these days, that you ask AI to help you write MATLAB code and help you build Simulink models. Now, I want to state first off here that as a student, your job is to learn. You need to understand some amount of theory and application and the inner workings of the system that you're going to design. And a great way to learn is to work through problems by hand and to code your algorithms from scratch. But industry wants to save time and money wherever possible, and doing something from scratch is often more time-consuming and more expensive than using a pre-built solution. And this means that you're going to be constantly faced with a question: how much should you do from scratch? And my advice is that in industry, whenever possible, you want to reuse as much as you can, or use tools that have pre-built solutions, because it can save you that time. And in fact, I'd argue that a lot of being a good engineer is using your knowledge to know which tools will help you get the job done faster and more accurately. Of course, there's bad tools out there, and Gen AI can create a lot of worthless slop, but that's why you're spending this time studying as a student and doing all of this work by hand, so that you're able to assess the output of your tools and have confidence that they're doing the thing that you need. So instead of thinking that you'll be creating everything from scratch in industry, just know that you're going to be using your knowledge to figure out the most efficient way and the most efficient tools to get your job done. All right, and speaking of tools, my last misconception that I want to address is that control engineering is accomplished using a programming language, and that you can program your control algorithms in any language, so the tools themselves don't matter as much as the knowledge. But the reality is that complex engineered systems require more than a programming language. As we talked about earlier, control engineering isn't just writing an algorithm. It involves building and validating models, simulating the full system, understanding how sensors and actuators behave, integrating with hardware and other software components, and iterating on all of this quickly and reliably. And trying to manage that entire workflow using only a general-purpose programming language can be inefficient and error-prone. And this is why the industry relies so heavily on MATLAB and Simulink. They're designed specifically for model-based design. With MATLAB and Simulink, you can create high-fidelity models and combine components and code from other languages like Python and C, and then everything runs in a unified simulation environment. And they also provide systematic ways to reduce those detailed models through linearization and other methods into forms that are ready for controlled design. And then once the controller is designed, you can generate production code directly from the model, eliminating the translation errors that often occur when hand coding an implementation. And they automatically generate reports and documentations and verification artifacts so that you can spend your time doing actual engineering rather than bookkeeping. So keep in mind that tools do matter. They're what allow you to work efficiently, explore ideas safely, and turn your engineering knowledge into reliable, testable systems. And so even if you aren't using MATLAB and Simulink in your studies right now, Hopefully you can see why they've become the standard tool across industry, and why a programming language alone isn't enough for modern engineering workflows. Okay, I hope you enjoyed this video on the 5 misconceptions about control engineering in industry. And this is actually a condensed version of a 35-minute webinar that I give to university students. And so I'll link to that below if you're interested in seeing the full, but slightly different presentation. All right, if you enjoyed this explanation, you can find all of the Tech Talk videos across many different topics nicely organized at mathworks.com. Thanks for watching, and I'll see you next time.